Welcome to this explainer. Whether you're a fresh student diving into FSC math, prepping for your DPE 803, or gearing up for competitive exams, you are in exactly the right place. We're going to demystify the core mathematical number systems from the absolute ground up. Math can kind of feel like a massive, tangled web of rules, but trust me, when we break it down visually, it becomes incredibly logical and, honestly, pretty beautiful. Today, we're taking a journey through the very fabric of math. Let's get right into it.
Here is our roadmap for today. We'll be layering concepts one by one. We'll cover 1, the universe of numbers, 2, the number line, 3, navigating math operations, 4, the imaginary unit, and finally, 5, complex number math.
Okay, part 1, the universe of numbers, building the mathematical Russian doll.
Think of number systems kind of like nesting Russian dolls. We start super small with natural numbers. Your everyday counting numbers like 1, 2, 3. But what if you have absolutely nothing? Well, we need a 0, right? Adding 0 expands our little doll into the whole number set. Now, what if you owe someone money? Suddenly we need negative numbers. That bumps us up a size into integers, encompassing all positive and negative whole numbers plus 0. Zooming out even further, what about slices of pizza? Fractions? That brings us to rational numbers, anything you can write as a fraction of 2 integers. But believe it or not, our universe doesn't stop there. So we have to talk about rational versus irrational numbers. The crucial takeaway here is that the massive set of real numbers is literally just a combination of these two working together. While a rational number can be neatly packed into a fraction, like m over n, irrationals, they absolutely cannot. They're messy, they're those wild decimals that go on forever without ever repeating. Think of pi or the square root of 2. Together, the rationals and irrationals form the entire set of real numbers. Honestly, pretty much every single number you've ever dealt with in standard arithmetic lives right here in this real number set.
Moving right along to section 2, the number line, visualizing real numbers.
So, how do we actually visualize these real numbers? We anchor them onto a horizontal x-axis and a vertical y-axis. This creates 4 distinct quadrants. Welcome to basic coordinate geometry. The x-axis gives us our left to right number line, and the perpendicular y-axis gives us our up and down number line. They cross right at the origin, which is 0. This simple visual grid forms the absolute foundation for literally all graphing and physical modeling in math. What's super cool about this is how every physical point gets an ordered pair. We assign positive coordinates to the right and up, and negatives to the left and down. Take point A, for example. It's sitting exactly at x equals 2 and y equals 3, so its address is the ordered pair 2, 3. Point B, it's down in the third quadrant, meaning it has a negative x of minus 3 and a negative y of minus 5. The x coordinate always comes first. It's basically like typing exact GPS coordinates into your phone, but for numbers. But what if we only care about how far a number is from 0, completely ignoring the direction? That's where absolute value comes in. Because this represents physical distance on our line, it is always positive. Meaning, the absolute value of both 3 and negative 3 is just 3. Think about it. Whether you walk 3 steps to the left or 3 steps to the right, you still physically walked 3 steps. The distance is a positive reality no matter what. All right, let's dive into section 3. Navigating math operations, your exam survival guide. Listen up, because this section is basically your survival guide for exams. If you mess up the basic traffic laws of numbers, the whole equation crashes. These are high-yield facts, especially regarding the tricky properties of 0 and 1. So many test takers get tripped up here. First off, 0 is an even integer. Why? Because it's a multiple of 2. Also, 0 is a multiple of every integer. And the number 1? 1 is an odd integer, and crucial point here, 1 is not a prime number. To be prime, a number needs exactly 2 distinct divisors, 1 and itself. Since 1 only has itself, it gets kicked out of the prime club. Memorizing these little quirks will absolutely save you valuable points on test day.
Now let's talk PEMDAS, the order of operations. 1, parentheses, 2, exponents, 3, multiplication and division, 4, addition and subtraction. The absolute most crucial point here is that multiplication and division have equal priority. You handle them together as a single step, going strictly from left to right. The exact same rule applies to addition and subtraction at the very end.
Applying the PEMDAS rulebook step by step keeps our math mechanics completely error-free. Take the expression 12 plus 3 times 2. If you're just casually reading from left to right, you might jump the gun and say, okay, 12 plus 3 is 15 times 2 is 30. No way. PEMDAS explicitly dictates we multiply first. So 3 times 2 is 6, and then you add the 12, giving us the correct answer of 18. If you actually wanted the answer to be 30, you'd be forced to put parentheses around the 12 plus 3.
Let's shift gears to Section 4, the imaginary unit, breaking the rules of real numbers.
We've mapped out all the real numbers. But what happens when the rules just totally break down? Any real number squared is always positive or 0. So how in the world do we solve an equation that results in a negative, like x squared equals -1? Think about it. 2 times 2 is positive 4. -2 times -2 is also positive 4. There is literally no number on our physical number line that multiplies by itself to give a negative. For centuries, this was just considered an impossible dead end.
To fix this impossible problem, mathematicians simply invented a workaround, the imaginary unit, I. This completely bypasses the traditional number line. They created a new rule defining I as the square root of -1. Therefore, I squared equals -1. It doesn't exist on our standard x or y axis. It lives in its own separate mathematical dimension, which suddenly allows us to solve equations that used to be impossible, a real game changer.
And we can actually bridge these two dimensions into what we call complex numbers. They are written in the standard form a plus bi. This seamlessly combines a normal real number, represented by a, like 3 or -5, with our new imaginary part, bi. It brings both worlds together into a single workable mathematical expression. Which brings us to our final section, number 5. Complex number math, operations with a plus bi. Let's pull out that PEMDAS rulebook again. Do our old rules still work when we throw imaginary numbers into the mix? The answer is mostly yes, but with one massive twist. Adding and subtracting is super simple. You just combine the real parts together and the imaginary parts together, separately. It's just combining like terms. But multiplying? That requires us to treat the expressions like binomials using the FOIL method, and we have to explicitly remember that whenever we get an I squared, we replace it with a -1. Let's trace out a multiplication example, 3 plus 5i times 2 plus 3i. Using FOIL, 3 times 2 is 6. The outer and inner terms give us 9i plus 10i, combining to 19i. Then the last terms multiply. 5i times 3i is 15i squared. Now, here's the magic trick. Because I squared is defined as -1, that 15i squared actually just transforms into -15. We combine that with our real number 6, giving us -9. So our beautifully simplified answer is -9 plus 19i. Finally, let's look at dividing complex numbers. The steps are: 1. Write it as a fraction. 2. Identify the denominator's conjugate. 3. Multiply the top and bottom by that conjugate. Basically, the conjugate is just a mirror image. If the bottom is a plus bi, the conjugate is a minus bi. When you multiply them together, all those messy imaginary I terms magically cancel out, leaving only a clean, real number on the bottom. It's an incredibly clever math trick that clears out the fraction. So we've expanded our mathematical universe today from basic natural counting all the way out to complex division. But it leaves you wondering, if imaginary numbers don't even exist on a regular number line, how do they help us solve very real problems? Well, it turns out that while I might not be on a physical ruler, complex numbers are absolutely essential for real-world applications like electrical engineering, quantum mechanics, and fluid dynamics. So next time you flip a light switch or use your smartphone, you actually have the imaginary unit to thank. Keep exploring, keep questioning, and keep mastering those fundamental rules.